Good morning. In the classroom last time, we stopped at the half-life of radioactive isotopes, and we were discussing the importance of radioactive iodine. And we said that radioactive iodine differs from the ordinary iodine in the mass number, which is 131, meaning that radioactive iodine has a greater number of neutrons in the nucleus, and you can get the number of neutrons by subtracting 53, which is the atomic number from 127 in ordinary iodine. This is the ordinary iodine, and this is the radioactive iodine that has 5 more neutrons. And since it has more particles in the nucleus, then it is more unstable, then it has higher energy. The nucleus contains higher energy to hold all these particles together, and therefore this nucleus will be unstable and will emit particles every now and then, or will decay every now and then. And the neutrons, as we said before, might emit, for example, negatively charged particles and be converted into protons. Here I added the diagram of the thyroxine hormone that is secreted by the thyroid gland. You know that the thyroid gland is a butterfly gland that lies here at the front part of the neck, and it secretes a very important hormone that is called thyroxine hormone that controls the metabolism and energy production in the human body. And thyroxine hormone is produced in two forms, a form where we have 3 iodine atoms and another form where we have 4 iodine atoms. So this form is called T3 or triiodothyronine, and the other form is called T4 or tetraiodothyronine. But you don't have to memorize the names. I'm just mentioning this because when you go to a lab in order to evaluate the function of your thyroid gland, you will ask them to measure the level of T3 and T4 in your blood to make sure that your thyroxine gland is working properly. Why are we using radioactive iodine for the diagnosis and treatment of thyroid diseases? Because since this element, iodine, is very important to synthesize the thyroxine hormone, then the thyroid gland will be avid to thyroxine, meaning that it loves taking thyroxine in large quantities from the blood, and it will be the organ that will take iodine in the greatest amount. And if it takes radioactive iodine, then you can scan the gland after that, because the molecules of radioactive iodine can be visualized and can be counted by means of an instrument that is called a Geiger counter. So if it is, for example, a cancerous thyroid, if you have, or the person has cancer thyroid, then the cells are dividing at a very high rate and they are uptaking thyroid. So you have a high uptake of iodine. You have a high uptake of this radioactive iodine. So it is used for diagnosis, but it is also used for treatment, because when the thyroid gland uptakes radioactive iodine, this radioactive iodine will decay and will emit particles and will give an amount of energy that is capable of destroying cancer cells. And in such a case, this is very useful because it is a specific treatment. Since the thyroid gland is the gland that takes iodine the most, then it will be the gland that will be destroyed the most by the radioactive iodine, and therefore you can avoid that other organs or tissues be destroyed by the radioactive substance, or like in chemotherapy, for example, that is non-specific. We can also use radioactive carbon, which is carbon 614, because it is easily visualized, as we said, and counted by the radioactive counter, Geiger counter. So why are we using carbon 614 in plants? Because you know that when the plants carry out photosynthesis, they produce carbohydrates. And these carbohydrates that are produced by the plant are sugars, and therefore they contain carbon as the important element that forms the skeleton of the molecule. So if the leaf produces a carbohydrate like sucrose, that carbohydrate will travel up and down the stem to go to other areas of the plant that do not photosynthesize. So if you want to visualize these carbohydrate molecules, not only to visualize them, but to know their number and therefore the rate or the number per unit time at which these carbohydrates are formed, then it's a good opportunity to use the Geiger counter. But if you use, how can we make sure that the carbohydrate that is formed by the plant is radioactive and that we can visualize it? By exposing the plant to radioactive carbon. You know that the plant absorbs carbon dioxide to photosynthesize. If you expose the plant to normal carbon containing carbon dioxide, it would give you non-radioactive carbohydrates. But if the carbon that is present in the absorbed carbon dioxide is a radioactive carbon 614, then all the carbohydrates that are formed by the leaf will be radioactive and can be traced in the fluid. And now we come to the concept of bonding. You know that atoms are neutral, but they are unstable because they want to reach the octet state. So you also know that atoms collide with each other and molecules collide with each other in a certain living system. And of course, if you give them more energy, more kinetic energy, they will collide more. Colliding is important for them to bond. And we have two types of bonding. We have, or the major types of bonding, we have the ionic bond and we have the covalent bond. We also have other types of bonds that we will be studying later on, like, for example, the hydrogen bonds. The ionic bonds are the strongest of all bonds, followed by the covalent bonds, followed by the hydrogen bonds. Ionic bonds are formed between two ions. Let's, for example, take the example of sodium 1123 and the example of chlorine 1735. Sodium has 11 electrons distributed on the energy levels, whereas chlorine has 17. So in sodium, we have 2 and then 8 and then 1 electron in the outer shell. So for the sodium ion, it is easier to lose this outer electron, to have 8 electrons in the outer shell and to reach the octet state. And that's why sodium is considered a metal. But in case of chlorine, which is 17, you will have 2 in the first shell, followed by 8 in the second shell, followed by 7 in the last shell. So it is easier for chlorine to gain 1 electron, to have 8 electrons in the outer shell, and therefore chlorine is considered a nonmetal. So if we have sodium and chlorine atoms in the same living system or in the same medium, then sodium will lose an electron that will be gained by chlorine. So when sodium loses an electron, it's no more neutral. It becomes a positive ion or a cation. And if chlorine acquires or gains the same electron, so it is no more neutral, but it becomes a negative anion. Once we reach this state of a cation and an anion, we will have a strong electrostatic attraction force between the positively charged cation and the negatively charged anion. And this strong electrostatic attraction force is called the ionic bond. But on the other hand, if we have two atoms that are non-metals, like hydrogen, for example. Hydrogen has one proton only in the nucleus, and it has one electron only in the outer shell. So each of these two hydrogen atoms requires one electron. So they do not usually, when they are together, they do not lose their electrons, although in other context, hydrogen may lose an electron, but in this context, they will not lose an electron, but they will share the electrons together. So if this first hydrogen atom and the other hydrogen atom share their electrons together, meaning that this pair of electrons will be revolving around the two atoms at the same time, this is what we call a this is what we call a covalent bond. So a covalent bond is a bond in which there is sharing of electrons between two atoms, and these atoms are usually non-metals. So just like an ionic bond can occur between a metal and a non-metal, but in covalent bonds, it is usually between non-metals. Why are covalent bonds strong? That's true, they are weaker than the ionic bonds, but they are still strong because the electrons, the shared electrons, are negatively charged, and the nucleus is positively charged. So the nucleus of each atom will exert some attraction forces on the shared pair of electrons that carries a negative charge, and at the same time, the other positively charged nucleus will attract the electrons, and this gives more stability to the two atoms. So stability, whether in ionic bonds or in covalent bonds, is first due to the fact that the atoms reached a full outer shell, because part of their reactivity is due to a non-full outer shell. So if they reach a full outer shell, they no more want to react, and because of the attraction forces that exist between the atoms that entered the chemical reaction. When the two atoms are when two atoms A and B are very far away from each other, they do not affect each other at all. But if these two atoms come closer to each other, then we will find that even if they do not form bonds between them, we will find that the nucleus of atom B will exert some attraction force on the outer electrons of A, and that similarly the nucleus of A will exert some attraction force on the negatively charged electrons of B. These attraction forces are not enough to make the two atoms come close together and make a bond, but they provide potential energy to the atom, meaning that the atom is always under stress because the atom feels that there is something that is attracting it, but it's not enough to make it reach the other atom. This is very similar to when you have a ball on your desk and then you raise it to a height h. It acquires a potential energy that is equal to mgh. As long as you're holding it, it doesn't fall. But once you release it, it will fall and will release the potential energy. So the potential energy is the energy that is stored in the atom because of its position. So because the two atoms A and B are in a position that allows the nucleus of each atom to attract the other atom, but not enough to make it too close or very close enough to make a bond, then they will have potential energy. But once, why am I saying this? You needn't know this in detail in AP biology, maybe in chemistry. But why am I saying this? Because once the atoms come close to each other and form a bond and become stable, they lose this potential energy. And the lost potential energy, so they lose potential energy. Once they lose potential energy, they become more stable. And all systems in the human, all living systems on Earth tend to be more stable. And being more stable, meaning having lower energy. So they will lose some potential energy, and this potential energy will be dissipated to the environment and will be converted to kinetic energy of other atoms and molecules that gain this energy and use it to move. So the potential energy that has been lost upon bonding will go to the environment and will provide kinetic energy to the surrounding molecules. You needn't understand the potential energy in detail, especially that I'm saying it too rapidly because it's not part of your curriculum. But what you have to say is that whenever a bond is formed, energy is released. This energy is the potential energy that the atoms used to have before bonding. So potential energy before bonding is higher than potential energy after bonding. And this potential energy will go to the environment. On the other hand, if two atoms form a bond together, then if you want to break that bond, then you have to supply energy. So bond making is associated with release of energy, and bond formation is associated with absorption of energy. Covalent bonds depend upon the number of shared electrons. So if you have only one pair of shared electrons, if we need only to share one pair of electrons, then it is a single covalent bond. If the two atoms need to share two pairs of electrons in order to reach the octet state, like in oxygen. For example, each atom requires two electrons to reach the octet state. So that each atom has to share two electrons with the other atom. In such a case, it would be a double covalent bond, and we will draw it like this. This is the first pair, and this is the second pair. But sometimes here, you know that carbon is tetravalent and needs 4 electrons to complete its outer shell. So carbon here is bonded to one hydrogen, so it needs 3 other electrons, and therefore it will share 3 electrons with the other carbon. So here we will have the first pair, the second pair, and the third pair, and the carbon atoms will share only one pair of electron with the hydrogen. And in such a case, we will find that the carbon atom is sharing 4 electrons, 1 with the hydrogen and 3 with the neighboring carbon atom. And therefore, if you count the number of electrons in the vicinity of each carbon atom, you will find it 8. So here we have a single bond, a double covalent bond, and here we have a triple covalent bond. And we said before that carbon is an important element in all organic compounds because of its versatility. And the versatility of carbon, or the flexibility of carbon, is shown by the fact that carbon can bind with carbon, but can also bind with other atoms, like, for example, hydrogen, like oxygen, like nitrogen. So this is the first aspect of versatility of carbon, that it binds with similar carbon atoms or hydrogen atoms or oxygen atoms or nitrogen atoms or whatever other atoms. The second aspect of versatility is the fact that carbon can form single bonds with itself or double bonds or triple bonds. And the same applies to other elements depending upon their valency. The third aspect of versatility of carbon is that carbon, and this is seen especially in fats, can form very long skeletons or very long chains of carbon. And these chains of carbon, so it can form short chains, of course, it can form medium length chains, and it can form very long chains of carbon. And these chains of carbon can be non-branched as the one you see here, or they can be branched like this. Now we come to the polar and non-polar covalent bonds. In case of oxygen, for example, let's see the example of hydrogen. We have a single pair of electrons that is shared. The electrons are equally attracted to the nuclei of hydrogen because here we have only one proton and here we have only one proton. So we have the same number of positive charges in the nucleus. We have the same number of positive charges in the nucleus, and they are similar atoms. So we have the same number of positive charges. We have the same size of the atom or the same atomic radius. And we also have the same electron shield, and we will explain this electron shield later on the corresponding slide. So the electrons are equally attracted, meaning that the electrons will revolve in the vicinity of the two hydrogen atoms equally, and they will spend an equal period of time around both. But if we come here, for example, to hydrogen and oxygen, we will have that we will see that oxygen will have a greater force of attraction on the electrons than hydrogen. And we will see why. First of all, because the protons here are 8 protons, whereas the protons here are 1 only. So there is greater attraction of the negative electrons towards the oxygen nucleus than towards the hydrogen. And this is not cancelled, as we will see later on, by the other factors. So we say that oxygen has greater electronegativity than hydrogen. What is electronegativity? It is the power of the atom or of the nucleus of the atom to pull on the shared pairs of electrons. So the electrons will spend a greater period of time in the vicinity of oxygen rather than in the vicinity of hydrogen in this OH group. This is not a whole molecule. So we say that oxygen will have a partial negative charge, whereas hydrogen has a partial positive charge. And we call this bond an asymmetric bond or an unbalanced bond or a polar covalent bond. Similarly, so before talking, we can see examples first because the example of water is very important. So if this OH bond is present in a water molecule, so here we have a pull on the electron towards oxygen, and here we have another pull on the electrons towards oxygen. This is the water molecule, OHH. This is H2O. So in a water molecule, the electrons from both pairs will spend a longer period of time in the vicinity of oxygen. So we say that oxygen has a partial negative charge. There is no gain of electrons, but it's a matter of the time that is passed around the oxygen. And here hydrogen has a partial positive charge, meaning that the electrons spend a shorter period of time in the vicinity of hydrogen. So we consider water a polar molecule. So although the two forces are equal, and we say although water is symmetric, meaning that I have an OH bond here and an OH bond here. I have a difference in electronegativity here that is equal to the difference in electronegativity here, meaning that I have a pull on the electrons here that is similar to the pull on the electrons here. However, although the water molecule is symmetrical, yet the two forces do not cancel each other. First of all, because they are directed towards each other, so they don't cancel each other. And second, because the molecule is not linear, the two forces are not on the same line. We will see that in carbon dioxide, for example, they cancel each other. The electronegativity of oxygen is 3.5. The electronegativity of hydrogen is 2.1. So the difference in electronegativity between oxygen and hydrogen is 1.4. So you might be amazed why the value of electronegativity of oxygen is not 8 times the value of electronegativity of hydrogen, since oxygen has 8 protons in the nucleus and hydrogen has hydrogen has hydrogen has 1 proton only. This indicates you that the electronegativity does not only depend on the number of protons, but it also depends on the atomic radius and on the electron shield that might affect the force, the mere force or the absolute force resulting from attraction by the protons. Of course, when we have many water molecules in a container, then if this is the second water molecule, it will also have a partial negative charge on oxygen and a partial positive charge on hydrogen. And therefore, there will be weak attraction forces between the partial negative oxygen and the partial positive hydrogen. And this weak attraction force is called a hydrogen bond. And although the hydrogen bond is weaker than the covalent bond and the ionic bond, yet it is enough to create strong adhesion forces, strong cohesion forces between the water molecules. It is cohesion because they are of the same type. And this cohesion forces that results from the hydrogen bond is responsible for all the very characteristic properties of water. And we will be discussing this later on. Let's come back to electronegativity. If we look at the molecule of carbon dioxide, this is the structural formula of carbon dioxide. The molecular formula is CO2. From the molecular formula, you can know what elements form carbon dioxide and in which number. But from the structural formula, you can know something more, which is the type and arrangement of bonds in the space. Here you can see that carbon is 612 and oxygen is 816. So if it were only dependent on the number of protons, then we should see that electronegativity of oxygen is higher. And it is the case, by the way. The electronegativity of oxygen, I shouldn't have said if it were due to this alone, because it doesn't apply here. But actually, oxygen has a greater electronegativity than carbon. So the electrons will be pulled more towards oxygen than towards carbon. And therefore, but since the two forces here are equal in magnitude, opposite in direction, and are on the same line, meaning that the molecule is linear, then they cancel each other. So again, why don't we say that carbon dioxide is a polar molecule? Although the bond C double bond alone is polar, and the other bond, C double bond alone, is polar. But the molecule as a whole is non-polar. This is because the molecule is symmetric, meaning that the forces on each side, the fact that the molecule is symmetrical results in the forces on both sides being equal in magnitude, opposite in direction, and because they are on the same line and the molecule is not only symmetrical, but also linear, so they cancel each other. This molecule of carbon dioxide that is nonpolar proves you that you might have polar bonds inside a nonpolar molecule. Now we come to the factors affecting electronegativity. We have the nuclear charge and the relationship between the nuclear charge and the electronegativity is a direct relationship because as the number of positive protons in the nucleus increases, the attraction on the shared pair of electrons will increase. And then we have the atomic radius, but the relationship between atomic radius and electronegativity is an inverse relationship. Why it is an inverse relationship? Because as the radius of the atom becomes larger, the pull on the electrons, on the shared electrons, will be weaker because of the huge difference that exists between them. When we come to shielding of electrons, if you have an atom that has a big number of protons, like chlorine, for example, that has 17 protons, this is not always in favor of electronegativity and attraction of the shared electrons, because this simply implies that the number of electrons is also 17, and therefore we would have 2, 8, and 7. And if there is a shared pair of electrons here, then the big atomic radius and the repulsion between the electrons will act like a barrier that will weaken the attraction force between the positively charged nucleus and the shared pair of electrons. So here we also have an inverse relationship. So the nuclear charge is not the sole factor that affects electronegativity because it might be cancelled by the other factors, which are the atomic radius or shielding. And the best example for this is CH. And CH is a matter of great controversy because many teachers say that, or in some books we say that CH is a polar bond because carbon is 612 and hydrogen is 1,1. But we have just said that it's not only the number of protons that affects, but other factors. So it's true that hydrogen has a smaller number of protons, and therefore it is supposed to have a weaker attraction on the shared pair of electrons, but it has two favorable factors that are not present in carbon. The first one is the smaller atomic radius, and the second one is the smaller number of electrons and therefore the smaller shielding effect. And therefore, CH finally is considered a non-polar bond. Here we can see examples, 3 examples of molecules. An example of a molecule where the bonds are polar and the molecule is polar. So HO is polar and the water molecule is polar, because although it is symmetrical, yet it is nonlinear. And in the other example of methane gas, which is CH4, by the way, CH4, each of the CH bonds is nonpolar. And we said that this proves that the number of protons is not the only factor that affects electronegativity. And of course, since each one of these CH bonds is nonpolar, then the whole molecule is nonpolar. And the third example is a polar, is the molecule of carbon dioxide where C double bond O itself is polar, but the whole molecule is linear. But the whole molecule is linear and the forces antagonize each other, and therefore the whole molecule is nonpolar. So the bond is polar and the whole molecule is nonpolar. So in water, both the bonds and the molecules are polar. In methane, both the bonds and the molecules are nonpolar. In carbon dioxide, the molecules are polar and the whole molecule is nonpolar. There is something that I want to say about the bonds in water. Now, if you look at the bond between oxygen and hydrogen, it is a covalent bond. It's true that it is polar, but it is covalent. But if you look at the bond between one water molecule and another water molecule, you would say that it is a hydrogen bond, and it exists between a partially positive hydrogen and a partially negative oxygen. And this is very important because you have a very important but simple question that you encounter on the test. So you have to differentiate between the intramolecular bonds of water and the intermolecular bonds of water. This is an I, by the way. And the intermolecular bonds. If we say intramolecular bonds, we mean the bonds inside the molecule, and they are polar covalent bond. But if we talk about the intermolecular bonds that exist between the partially positive hydrogen and the partially negative oxygen, then they are hydrogen bonds. Okay, this is very important. Here you can see the example of carbon dioxide where the molecule is symmetrical and linear. In case of sulfur dioxide, from this arrow, you can deduce that the molecule, that we have two equal forces, but the two forces do not cancel each other. The two forces do not cancel each other. And why don't they cancel each other? This is because the molecule is non-linear, and therefore you have a part of the molecule that is partially negative and another part of the molecule that is partially positive. In case this is what we call sulfur dioxide, because you have a sulfur atom and two oxygen atoms. So it is a bioxide or a dioxide of sulfur. And then we have hydrogen fluoride. Hydrogen fluoride, which is H with a bond F. Hydrogen fluoride, where we have a bond between hydrogen and fluorine, you can see that fluorine has a greater electronegativity and that the electrons are pulled towards the fluorine. So the hydrogen fluoride gas is a polar molecule in which fluorine is partially negative and hydrogen is partially positive. In case of sulfur, the electronegativity of sulfur is around 2.5. Whereas the electronegativity of oxygen is around 3.5. That's why the electrons are pulled towards oxygen, the shared pair, and therefore the partially negative is the oxygen and the partially positive is sulfur. We will stop here and then we will continue on the next video.